Right, okay. Over a period of about 2 or 3 months, no, 3 months at least, we ported VFX Forth to 64 bits. Now, this was on x86 to x64, and we sort of went from simplicity to horror and back again. The horror comes from realizing just that the compatibility of 64-bit x86 is not as wonderful as one might have hoped, and the number of nastinesses in the instruction set is quite spectacular. So what did we actually do? Well, all MPE Forths have a cross-compiled kernel. At least all the desktop, all of them have a cross-compiled kernel. So we first thought, let's avoid a port one stage of the port, and we'll use a 64-bit existing 64-bit Forth as the cross-compiler host. Unfortunately, MacOS was a second-class citizen, and the client who was actually sponsoring this needed MacOS as its first target. So we reluctantly used the existing VFX Forth 32-bit edition as the compiler host and put up with the problems with literals and addresses. The first cheat was that, unlike we worked out that it is possible to run stuff on macOS below the 4 GB boundary. So we did that, and then most of one's addressing problems on a 32-bit host go away. So having got that far, we then, once the first target was stable, we ported the x64 assembler, disassembler, and code generator into the fourth target. Oh Christ! So how did I change size? So we ported this x64 assembler, disassembler, and code generator, and then we ported the x64 cross-compiler itself onto its 64-bit host, and then we ported the ARM Cortex cross-compiler, so that we can now run that under Catalina, which was the objective of the client. So the conversion stages were really the 64-bit assembler and x64 assembler and disassembler. Then we ported the VFX code generator and the shared library interface, floating point, and then we were porting most of our 32-bit code onto a 64-bit host and testing as we go. AMD is supposed to be upward compatible, but not quite. But anybody who's been through this once or more will know that you end up dreaming of a Rex byte. The Rex byte is the change to the instruction set, has the big impact. It removes the short form INC and DEC instructions from x86 and reuses it for its own purposes, known as the Rex byte. I shall remember 4X as for the rest of my life, probably. But basically, the Rex byte selects has one bit set if you're using 64-bit data, and then another 3 bits that determine the upper address, the upper bit of the register selection so that enables you to use R8 to R15, because we now have 16 registers rather than 8. Other things to remember is that not all instructions have 8, 16, 32 and 64-bit forms, so there are a lot of special cases. AMD is mostly consistent, but not always, except when it isn't. So the special cases are the bits are the parts that make the pain. The byte register selection, effectively using what you used to call AL, BL, and so on, is affected by the presence of the rex byte. So in practice, it's too much of a pain to use AH, BH, CH, and DH, so you can now treat the 16 registers as the only byte registers you really got are the bottom bytes of these 16 registers, which is just like every other processor. You've only got 16 and 64-bit pop and push, so 32-bit doesn't really work. Registers need 4 bits, and as I've explained, one of those bits is in the rex byte, and 3 are in either the mod RM or SIB bytes. If this is meaningless to you, it's about the way the x86 instruction set is encoded. Unfortunately, the mod RM byte is only partially decoded, whereas the SIB byte is fully decoded. And in particular, a consequence of this is that R12 and R13 are bloody dangerous if you get it wrong. And as we did, which we did get wrong because we used R12 and R13 for our own particular purposes. Literals become a little peculiar. You're partly rescued by the mod RM encodings, but you can really only have 32-bit literals unless you use the magic special purpose 64-bit put a literal in a register instruction. So in the long term, the encoding is much more than x86 with 16 registers. It's also a bit less. So it isn't quite as nice as advertised, and you end up reading a lot of special case footnotes in both and if you don't read both the Intel and the AMD notes, you're likely to get something wrong. So the code generator followed on from once you've got an assembler and a disassembler, you can test the code generator. That was actually the least difficult part of the job, because by the time you've done the assembler, you know what's going to bite you, and the literals are really become the place of pain, because as you now have 3 different cases: literals that can be 0 extended at 32 bits or less, and literals that can be sign extended at 32 bits or less, or we really need 64 bits. The reason you don't really want to go to 64 bits is that the instruction is huge. Loading registers takes you 9 or 10 bytes. So the absolute addressing has disappeared. You now have to use PC relative plus with a 32-bit displacement instead. But apart from that, you end up just extending the VFX code generator tables for extra registers, and then you have to cope with a few other special cases, which are to do with sign extension in pain. There's a particular new instruction, MOV SXD, that becomes part of your life. So the next phase is, now we've got a code generator, which of course we're trying to test. So you run all your test suites. So we're at the place now that the code generator, we have a stable code generator. The cross compilers work, the interface to Cocoa works, DocGen works. So essentially all our basic heavyweight tools actually work. So what we're going to do next is clean up after the port. We're now into beta phase. We make more use of the extra registers. For now, they're part of the resource lists, and people who have experience of VFX Forth in the 32-bit will notice that it doesn't shuffle the stack nearly as much as the old one did. So that which is a performance improver, but the code is bigger. Cache they will cache the top items of the return stack in registers because we can take 2 away without anybody noticing, and we'll do a floating point optimizer for SSE instructions, and then we'll make our final decision as to which floating point system to use. The shared library interface, we were lucky at this stage. macOS and Linux use the same interface to shared libraries, or they use the same ABI. It's register based. You can use 6 integer and 8 floats. You can return more than one item, which is nice for the people doing graphics, because a point is returned as one item, or rather as 2 XMM registers. So you can put floats and doubles, but we then came to the point where the guru who looks after the Cocoa interface really doesn't like reading C at all. He essentially refuses to do it. So what he wanted was an interface mechanism, unlike our existing extern interface, but that's what he wanted, and that's what he got. And actually, it's a potential for standardization, because it's the least effort implementation for nearly all Forth systems. So we could actually get some close. The extern interface is something we developed many years ago, and we've used it for years and years, and it copes with all the horrors of interfacing to C. It copes with argument promotion. It can return known types. The user can add types to it, and so on and so forth. So here's the examples. Here are mixed integer and float. The 2 above are part of the Cocoa interface, but Rolf wanted a Forthy interface because what he wanted to focus on with the stacks. He wanted to focus on the Forth data stack and the Forth floating point stack. So up here you see the extern version of it, which is basically put extern : in front of the C declaration, having made sure you know about the relevant types. To do this in the way he would want it, because he was porting the Cocoa interface to more than one Forth, is to define the parameter lists as their Forth stack behavior. So you've got here, you're passing a context, and what you get out of the first function is an XY pair as floats, as double floats. The second one is essentially its inverse. The other things you have to watch out, and this is the bit where I don't like this kind of function : interface, is because if you only permit 64-bit integers or 64-bit floats in your interface, you now have no way of knowing how a Boolean is returned by the operating system, which could be 1 bit in 1 byte. It could be a byte of 0 or 1, or byte of FF, or it could be a 32-bit int or a 64-bit int. And sometimes the operating system people change their minds. And at one stage, many moons ago, Microsoft changed the way they returned an atom and things got messy, but we only had to change the extern interface and everything else got fixed auto-magically as a result, because all atom handling went through this one place. So we won there. But although this type of interface with the Forthy interface looks attractive, you have to be aware that there are a number of problems inherently associated with it. Porting 32-bit code to 64 bits was a pleasant surprise if you prepared enough, and I was pleased to note Nick's comment that you really do need to prepare to do this, because you need to factor out things like the cell words for where you mean. And remember that as Nick already pointed out, for macOS and Linux, an int is a 32-bit item, a long is a 64-bit item, and a pointer is a 64-bit item. And then we hit the real pain. The macOS signals essentially were easy. The conversion, everything, because the BSD and the OS X people hadn't changed very much, and where it was obvious, they just promoted 32-bit stuff to 64-bit stuff. So the amount of structures that we had, the proportion of structures that we had to change was minimal. In Linux, they'd taken the opportunity in going from 32 to 64 to change a lot of things, and they assumed that if they were going to bleed, we were going to bleed. So Linux signals were a real pain. The problems are in the C header files, and the chains of obscure headers and changes of notation are a real pain. Utterly horrendous. I really don't want to do that again, and we're going to have to go through it all over again with Windows, because we haven't done Windows yet, because Windows uses a different interfacing scheme into the to the operating system. So we thought what we'd do is we'll get the Windows, if we get Linux and macOS stable, we're on a very good starting point to do the Windows one. Really, you have to know your data. You really do have to check everything. Our nastiest port failure was when we in the ARM Cortex cross compiler. We have an interface to the ARM procedure call standard for the ARM Cortex 32. This allows us to interwork between C and Forth, so that ARM targets can call C code. On a 32-bit cross compiler, the implementer had made assumptions about data size which were wrong. On 64-bit, it took us about a day or so to find this and 5 minutes to fix it. So it's really a question of, as always with a cross compiler, you have to know what's referring to the host and what's referring to the target, and trying to use the same words for both really doesn't work well, or at least not with my brain. And of course, with this particular application, the app was client mission critical. So, you know, the screams lasted a while. You can always do better with testing, because the problem with testing is that you shouldn't be making these mistakes in the first place. So testing is really just finding out the things that you got wrong. So we try to find the residual bugs. You fix bugs before you do anything else, and regression test helps because we all make mistakes, and test suites are a lifesaver. And and I have to say thank you to John Hayes and particularly to Jerry Jackson, because it's mechanical and it saved us a lot of time. So here's an example of a macOS VFX Forth for macOS app. This is a mapping interface, a program called MyMaps by Rolf Toxopius, and it just works. It really is quite magical. But what else can I say? Thank you, Rolf. So the VFX Forth 64 exists because of these people. They either contributed things, or these are the alpha and beta testers for for us, and they have our considerable thanks. And that's it. How am I doing for time?
Oh, very fine, very fine. So
any questions?
You actually made up for the overrun of the last session. So Nick Nelson, please.
Can I just double check, first of all, Stephen, that externs are still here to stay? Because I didn't like the look of the so-called Forthy interface there.
Oh, they're very much here to stay. Externs are good. The Forthy interface is going to... They're welcome to have it because they're going to bleed. But the extern interface is... I mean, the point is that the extern interface is a lot more code. It's a place where you soak up a lot of problems, and it's not nice. But it's intrinsically a complicated problem.
Yeah.
And you might as well put in the effort to fix it.
Okay. And I don't know if you remember, but we did have some problems on the ARM, on the 32-bit version, when you had, I think it was more than 6 floating points in the parameter list. With extra registers, is that going to go away?
Well, it already has gone away because you've got 8 registers, but also because we had that experience, we also were much more careful about not assuming that people would write silly code.
Thank you very much.
And I say nothing about who wrote it, but I mean, it unfortunately, especially with the Cocoa interface, you do get huge parameter lists and lots of floats, so you're likely to be safe.
Thank you very much indeed.
Bernd?
You said the 64-bit absolute addressing went away, but that is not quite right because you can use one mode to AX or AX.
You have a MOV. You have a MOV. There is a MOV abs instruction, but if you start counting bytes, you'll wish you hadn't.
Yeah, it's just 64 bits. It's long, of course. The instruction itself is not so. It's not so much longer. It's just the 64
no. The
bits.
difference, yeah, but it's not a replace. It's in no way a replacement because the x86 and hence the AMD64 is essentially a register to memory architecture, and the 64-bit addressing is only available in one form.
And it's only for one register.
It's essentially one register, one instruction. So it's not as useful. It's not a bad way to deal with I/O ports, I suspect.
No.
But that's I think is all it's there for.
I don't know what it's there for.
Yes, I have to relay 2 questions from Twitch, please. Any perceptions on speed or memory size changes in the apps built on the 64-bit environment?
Okay, on speed, there's the benchmark tests suggest suggest that there's a 3% slowdown, which I'm told is quite good for 32 to 64-bit conversions. The problem is that since Forth is cell-based, there's a lot of 64-bit handling, and therefore you get a lot of Rex bytes. So the code is going to be a little bit bigger. I mean, 5, 10, 15% bigger.
And the second question from Twitch was...
Hang on, I haven't finished the first question. So that on the other hand, you do get enormous, really good improvements if you're using data, 64-bit data, or 128-bit data, because the complexity of that sort of stuff is far less than it ever was in 32-bit world. So that's really the code. Yes, it's the other place we're seeing a lot of lost size is in the Forth headers, because at the present they're all about 64-bit flat addresses. Whether we decide to change that in the future, I'm not sure, but in a sense, memory usage is almost irrelevant in the world we live in now. So I'm tempted to leave it as it is.
Yeah, next question, Gerald, and then Nick, and please a short answer because time is running out.
Okay. Any advantages gained by the app by going 64-bit outside of operating system support?
Very little.
Very good short answer. Nick.
Yeah, I just had a total panic there when somebody mentioned relative addressing, but I guess, can you confirm that this is transparent to the applications programmer?
Well, you haven't broken it yet, so
I
yes.
haven't got totally fast.
all your variables and values are affected, so it all works.
Variables? What are those? I'll tell you what to do with those later.
All right, so thank you.